Hello, chemist and biochemist. In this video, what I'd like to talk to you about is I'd like to talk to you about the sugar glucose, and I'd like to focus on the cyclization of glucose. Now, generally, whenever you look at glucose for the first time, you look at it as a linear molecule. Well, that's not really the most biologically relevant form of it. It's instead going to usually form a six-membered ring. Now, it can form a five-member ring, it can form a seven-membered ring, but the most common form that glucose is going to take is this six-membered ring that we're going to look at right here. So first and foremost, this is your linear form of glucose. Now, what we see on this linear form of glucose are a couple of things that make it, I don't know if I would say unique, but that are particularly relevant to the cyclization of glucose. First of all, that partial positive charge on our carbonyl carbon. Now, that partial positive charge makes this molecule susceptible to any sort of, attraction to a negative charge. Now, one thing that I did forget to draw right here, which is a little bit of foreshadowing, is my hydrogen on my hydroxide group on carbon number 5. So I'd like to draw my numbers 1, 2, 3, 4, 5, and 6. Okay. Now, whenever we talk about this cyclization of a sugar like glucose, we need to talk about the functional groups that are relevant. Well, the relevant functional groups are an aldehyde and an alcohol. Now, if you look at glucose over here, I'm going to put a little star by all of the alcohols. So if we need, for the cyclization of glucose, an alcohol and an aldehyde, arguably there's like, well, 5 other places or 5 other groups that could react with this aldehyde. But what I'm going to focus in on is I'm going to be focusing in on carbon number 5 and the hydroxide group on carbon number 5 and its reactivity with the aldehyde functional group. Now, what's going to happen is that this alcohol has lone pairs of electrons on that oxygen. Those lone pairs of electrons are going to be attracted to that partial positive charge on our carbonyl carbon. What that's going to do is that's going to lead to electrons going from our double bond to that oxygen, and ultimately leading to these electrons, these excess electrons, picking up a hydrogen, either this hydrogen down here on this alcohol, or one basically from a protonated base somewhere else in the environment. Now, what this is going to lead to, and the numbering, I wrote these out because that's particularly important whenever we talk about glucose cyclization, is we've got, and I'm going to start with carbon number 6. The reason I'm starting with carbon number 6 is because it kind of stands out. First of all, that is going to be the carbon that is outside of my ring. So I'm forming a 6-membered ring, but only 5 of the members are carbons. 1 of them is an oxygen. Carbon number 6 is not in my ring. Instead, it looks like this, CH2OH. Then I draw down to what is carbon number 5. Carbon number 5, I'm going to go ahead and draw not a non-skeletal structure here. Carbon number 5 has a couple of different bonds. One, so I'm going to scribble in the one that I just drew. I'm going to draw a bond to an oxygen because, well, it still has a bond to an oxygen. Okay, so there's that bond that I just drew in. Now that oxygen, I'm going to go ahead and move, I guess, in a clockwise fashion. So that oxygen established a bond with a carbon. That carbon is right here. Carbon number 1. Okay, so this is 5, this is 1, this is 6. So I've counted for 3 of my carbons. My remaining carbons are going to be, and let's see, my remaining carbons are going to be carbon number 2, which I will scribble in that bond on my linear form. Carbon number 3, carbon number 4, and then finishing my cycle to carbon number 5. So I've got this general ring structure. Now, what's important to note about all of these different atoms or one thing that's important to note about all of these different atoms that are in my ring is if you look at carbons number 2 through 5, one of the things that's worth noting about them is that those are all chiral carbons. Those are all carbons that are bound to a total of 4 different things. If you look at carbon number one in the linear, specifically in the linear form of this sugar, is bound to 3 different things. It has a double bond to an oxygen, a single bond to a hydrogen, and is a single bonded to a carbon chain. Well, the thing is, this double bonded oxygen, well, that double bond, those electrons that made up that double bond, some of them were forced out. And when they were forced out, they picked up a hydrogen from a protonated base, in which case that double bonded oxygen became an alcohol. So we didn't change the carbon hydrogen bond. I'm going to put that down here. But we did take that double bonded oxygen and make it an alcohol. So carbon number 1, when we cyclize a sugar like glucose, has gone from a carbon with 3 unique bonded things to 4 unique bonded things, meaning this is a chiral center. Specifically, it's a new chiral center. 2 through 5 were chiral centers, and they'll remain chiral centers, but 1 was not a chiral center, but is now. Now, I'm going to go ahead and add in a new chiral center, and I'm going to qualify that and say that use the term for this. This is known as the anomeric carbon. Also worth noting about this cyclization event is our reactive groups, our aldehyde and our alcohol. Well, our aldehyde and our alcohol, those react together to form what is known as a hemiacetal. If by chance you're a fan of movies from around the year 2001, you might be a fan of the movie Joe Dirt or Joe Dirte. And well, this would be Joe Dirt's favorite type of functional group because it's a hemi. It's got a hemi. Anyway, I digress. Okay, so back to our ring structure. We've accounted for carbon number 1. We've accounted for carbon number 6. We have partially accounted for carbon number 5. And the reason I say partially is because the only thing that we didn't include is we didn't draw our hydrogen bound to carbon number 5, but I assure you it's there. Now, what we need to go on to from there is carbons 2, 3, and 4. So I'm going to put a check mark by, or put a star by 5. I'm going to go to carbon number 2. And if you look at glucose, carbon number 2 has a hydroxide group on the right-hand side. Carbon number 3 has a hydroxide group on the left-hand side. And carbon number 4 has a hydroxide group on the right-hand side. Now that is significant. The positioning of those hydroxide groups is very significant. If this had hydroxide groups on the right-hand side for all of the carbons, that would make this a particularly unique sugar. That would make this an isomer of this molecule that we're looking at right here. So it's going to have a different functionality. It's going to be, from a biological perspective, it's going to be metabolized different. And so what that means, or what I want you to take away from this, is just as when we draw it in a linear sugar, or just as when we draw a molecule in the linear form, and we're considering a positioning of hydroxide groups, we need to do the same thing when we're cyclizing it. The way that I always think about it is, if the hydroxide group is on the right-hand side of the molecule when it's linear, then when it's cyclized, it's going to be pointed downward. And so what that means is carbon number 2 has a hydroxide group that's pointed downward. The opposite is also true. Well, if it's on the left-hand side, it's going to be pointed upward. So on carbon number 3, hydroxide, hydrogen. Carbon number 4 is going to have a hydroxide group pointed downward, and the hydrogen upward. With that said, we've completed our molecule. This is what we're looking for. This is our cyclic form of glucose. Now, the one thing that I addressed but didn't really go into um, specifics on is our new chiral center. Well, a new chiral center, our anomeric carbon, is very significant. It's very significant because if you have the hydroxide group pointed upward, as you do right here, um, that would be considered the beta form of this glucose, or the beta form of glucose. Now, if you have a hydroxide group pointed downward, as I'm drawing right now, that is the alpha form. So if you wanted to kind of capture this right here, and I'm not going to edit it anymore, this is the alpha glucose. Now, what you're looking at right here is an alpha sugar, an alpha glucose. It has a reactive center where that anomeric carbon is, because what can happen is that this ring can open up, and what can be observed is a phenomenon known as mutarotation, where the sugar interconverts between the alpha and the beta configuration. So this ring will open up, and that hydroxide group that's pointed downward will rotate. The sugar will close, or the ring will close up again, and the hydroxide group is pointed upward. So it can interconvert between the alpha and beta forms. Now, that is what is known as mutarotation. This six-membered ring here is known as a pyranose. I said previously that glucose, for example, could form a five-membered ring. Well, if you have a five-membered ring, that is a furanose. Um, so those are based on the functional groups pyrans and furans, or pyran rings and furan rings. At any rate, I hope this was helpful. I hope that you gained an understanding of each of these components, the cyclization event, the different groups, and I hope that your understanding of cyclization of something like glucose is a little bit better. All right, well, have a good one.